joining us today. I do want to mention that this program is going to be recorded, and after allowing us some time to process it, you can find it on our website in our video library. I do want to mention that credits are only available to those who are attending this live, but certainly if you want to check back in the video library and double check information or refer some of your colleagues to it as an informational resource, it should be there within a day or two. So you are welcome to access it from the video library. I want to get the program started by thanking Potomac Edison and Willdan's very much for providing this program. I also want to thank them for being a silver sponsor of AIA Potomac Valley and being such a strong supporter of us and being a very vital part of our community for several years. We greatly value the partnership that we have with them and the compelling programming that they provide. So without further ado, I am going to hand this off to Amy Lohman, who is Potomac Edison's Commercial and Industrial Energy Efficiency Program Manager. Amy is going to get us started. And Amy, the floor is yours.
All right, thank you, Sue. And as she mentioned, I'm the CNI Program Manager located in Maryland. I want to give a thanks to everyone for joining today. If we go to the next slide, I just want to talk a little about the programs that are offered to all Potomac Edison, Maryland customers. We have a variety of programs that are eligible for customers big and small, any type of facility. So if something's listed here and you have questions about any of these programs, you can feel free to visit the website listed here or reach out to me or the Willdan team, and we can put you in the right direction. But today we're going to be talking about commercial new construction. So I will turn it over to Sarah to take us through.
Thanks, Amy. Hello, everyone. I'm Sarah Mills, a member of the outreach team at Willdan. Today, I'm joined by my colleagues Annie Hu, an energy specialist, and Han Pham, our program manager, who can address any technical questions and program questions. Here are a few more details on the Commercial New Construction Program, or CNC. Our intention is to provide assistance to Potomac Edison customers, architects, and engineers while a project is still in design and there's still time to consider different energy efficiency strategies that could be incorporated in. We provide this assistance through our complementary energy modeling services. The model will show a range of energy savings opportunities as well as a range of energy incentives for the customer. These energy incentives can help you reduce costs of implementing strategies that go beyond the energy code. And by participating in the program, customers and design teams will have access to our team of consulting engineers. In terms of eligibility for the Commercial New Construction Program, projects do need to be within Potomac Edison's service territory. We accept commercial projects that are either new construction, major renovations, and/or additions that are at least 5,000 square feet. Participants do need to be interested in evaluating the energy efficiency potential for their project, and projects do need to get enrolled while still in design. We'll accept projects that still haven't completed their HVAC construction documents. We also want to point out that there's no cost to participate in the CNC program, and that energy incentives are available to both the customer and the design team. I'm happy to answer any questions about the CNC program, and you are always welcome to reach out to myself or anyone at the Willdan team for more information, or of course, visit the link on the screen, energysavemd-cnc.com. Perfect. So this course has been approved by AIA. Upon successful completion of this course, reporting for AIA members will be provided along with a continued education certificate for those who request one. This course has been approved by GBCI for one general continued education hour. Upon course completion, lead professionals can request a certificate for self-reporting to GBCI as well. And here's the agenda that we've set out for you today. First, we'll set the stage with some key terms and concepts. Then we'll dive into the energy analysis exercise in which we'll take a real case study and run a few what-if scenarios to evaluate different conservation strategies. After that, we will reveal the built project results and review some key takeaway concepts. Throughout our presentation today, we'll be doing a few polling questions. I'll give everyone a moment here to either type in this URL or use your phone to scan the QR code, and we can test the poll to make sure that it's working. So I'll leave this slide up for a few moments just to give everyone a chance. Okay, great. So here we are. We're testing the polling app with this question. What superpower would you like to have the most? And I do see some answers coming in, so perfect. It appears that the poll is up and running. So feel free to keep your phone or browser on this page. We will be using it a few more times throughout the presentation. Awesome. So let's get into the course. Why is energy efficiency important? And how do we get to a clean and cost-effective energy future? We know that reducing energy consumption of the built environment is vital to success. And as design professionals, we have an important role to play in cutting consumption. So could it be as easy as adding solar to every rooftop? Unfortunately, adding renewable energy generation without first implementing energy conservation measures can have detrimental impacts to the grid. This is why we need to exercise our creative problem-solving skills in order to reduce the load of the building as much as possible. Okay, time for another polling question. Typically, what do you utilize to help make decisions with regards to energy efficiency? Rules of thumb, manufacturer's literature, comparison to other buildings, or an energy model? Interesting. Cool. Seeing some answers come in. So while we're at it, one more poll question. What types of projects tend to implement more energy efficiency measures? Multifamily, institutional or office, retail, or industrial? And I'll give us another minute to make sure everyone's had a chance to submit. Cool. Yeah, so this is somewhat of a tricky question as there are really no rules to follow in terms of this type of project. It really depends on your building type and what budget the owner has. It is, however, somewhat of a trend to see institutional buildings implement more energy efficiency measures since they tend to be the least interested in shorter paybacks. Cool. So in our discussion today, we'll be talking a lot about EUI. For those of you who aren't as familiar with it, EUI is a key metric to understanding how buildings use energy. It's measured in kBTUs per square foot per year, and you can consider it similar to MPG in a car, but in this case, you want the lowest number possible. How does that work? We take all energy needs in a project, heating, cooling, lighting, and anything that makes the meter spin, and divide that energy consumption by the square footage of the building, which normalizes the value independent of the size of a project. So that way we can compare the efficiency of a smaller building to that of a larger building on a per square foot basis, and that resulting number is the EUI. You might be familiar with the difference between site EUI, which looks specifically at on-site energy consumption, and source EUI, which also takes into account efficiencies in generation and transmission. But for today, we're keeping it simple and just looking at on-site energy. Just know that if you're involved in energy studies and comparing different projects or results, that you know which EUI you're using, just to keep your comparison as apples to apples as possible. So again, how do we get to a clean and cost-effective energy future? It's hard to say, but reducing the energy consumption of the built environment is vital to the success. And as design professionals, again, we have an important role to play in cutting consumption. Could it be as easy as adding solar to every rooftop? Like we said earlier, adding renewable energy generation without first implementing energy conservation measures can have detrimental effects to the grid. So far, we've talked about energy in the big picture, on the grid and at the site. So now let's move into the building and talk about efficiency. As an example, here are a few energy efficiency strategies you might consider. And here's some more and more and more, and pretty soon it's overwhelming and you don't know where to start. So how do you cut through all of that and see what makes sense for your project? Let's build some structure on how to find the right strategies. One place to start is to know what your goals are. Are you trying to reduce costs for your client? Do you have a lead goal? Or maybe you're trying to get net zero? Each one of these goals can send you down a very different path with your design. And the first step is to know what your goals are. Now that you've identified your goals, it's time to strategize. But how do you choose the right strategies? We did a poll on this earlier. Oftentimes, teams will depend on rules of thumb or maybe the manufacturer's literature, or maybe we compare two similar buildings. You can see where this is going, just down a rabbit hole of endless possibilities. But luckily, we can help and instead leverage energy models to do the work for us. So when utilizing rules of thumb, manufacturers' literature, and considering EUIs of other buildings, it's important that you compare apples to apples. Here on this slide are some variables to consider to ensure that you're doing so. And an example of this is our team compared two project locations from the same retail chain. The building layouts were identical, with the only difference being one building was reoriented by about 45 degrees. And it was surprising to see how different the energy usage results were, as you would think that both locations would have the same results since both buildings had similar footprints and operations. However, due to the orientation of one of the buildings and the window placement, more energy was being used due to heat gain from the sun, and as a result, the energy savings and incentive were lower. So unless cost is no object, you aren't trying to get the best, most efficient building out there. You're just trying to balance first costs and savings against your goals and looking for that sweet spot with the group of energy conservation strategies that gives you the biggest bang for your buck. So when to start? You have the greatest opportunity to maximize your savings when you start early on in stages like schematic design and design development. First, by minimizing the energy load through efficient massing and judicious use of glazing, followed by implementing simple, cost-effective systems through the HVAC design and lighting. Applying these measures will minimize your base load and have less impact to the grid. But of course, you do have to remember that at the end of the day, the building is going to be operated in ways that we can't always predict. Finally, we can discuss what goes into a comparative analysis. We'll consider several variables like building geometry, so the square footage and building type, then the operation and weather, so the hours of operation of each space, assumptions on how the building is going to be operated and occupied in an average weather file for that area, and then minimum requirements like HVAC and plug loads. All of these factors are then compared against the minimum requirements of the code baseline, which ultimately produces the energy model results. But with everything that goes into these models, it's important to remember that combining the effects of energy efficiency strategies isn't straight addition. In this case, 2 plus 2 doesn't always equal 4. And that's because we have a whole building and systems approach. We then need to factor how these strategies interact with each other. A good example of this is using LED lighting, which generates less heat, which in turn reduces cooling loads in the summer, but it increases heating loads in the winter. Since those loads aren't perfectly balanced, the net result is somewhere in between, and it takes a comprehensive energy model to identify how exactly that plays out. So for the purpose of today's discussion, we've narrowed our energy model down to 6 categories to review. And here they are. Massing, envelope upgrades, lighting controls, HVAC system, demand controls, and energy recovery. So here's some background information about the project that we're going to be using for today's exercise. It's based on an actual project that came through our office. It's an elementary school with typical programming and uses and typical hours of operation. So keep in mind that only parts of the school are occupied during the summer months. The case study project is located in the heart of the Midwest, climate zone 5A circled on the map there. So think really cold winters, hot summers, and short shoulder seasons. So let's get back to our poll. We're going to give you a pop quiz. Let's say it's day one of your project and the owner says, what should we do? So no background here, just kind of looking for a gut reaction on which combination of strategies might add up to an efficient project. So on your phones or on that polling website, you can choose A, B, C, or D, depending on which combination of the strategies on the left might have the most impact. We'll give you some more details on this later and see how your response might change, but for now, just your best educated guess. Great, looks like B is the more popular choice. Cool. We'll return to this one later. But now let's think back to those 6 energy efficiency conservation measures that we talked about a few minutes ago. Right now, we're going to go through each one of those strategies, review the options you'll have on the table, talk about some of the energy data you'll use to inform your decisions, and then we'll let you select which option you'd like to use in each category. But not all energy strategies cost the same, and we all know that every project has budget constraints, so we will need to keep that in mind. So we'll show each option with its related cost in dollar signs just to simplify the exercise. So let's say we have $12 to spend on energy efficiency upgrades. The first option here on the table is building massing. On the left is the base option. It's a floor plan focused on views, daylight access, and visual interest for the occupants. The alternate on the right has the same square footage and the same program, but is more compact, has fewer windows, and of course costs less to construct. And then out of these two options, they both have their benefits. The dispersed option may be better for user experience and could save money on lighting if daylighting controls are factored into the design, but it will have more heat transfer, so the HVAC system will have to work harder than if the compact form was implemented. Another decision we'll be looking at is the makeup of the envelope. Are we using fairly basic insulation and glass on the left, or are we upgrading, perhaps adding a layer of continuous insulation on the walls, cutting down on thermal breaks, and thicker insulation on the roof? Paired with that, we're looking at a reduced solar heat gain glazing to cut down on cooling loads. But as we know, designing for increased insulation and adding more efficient windows can be expensive. So the upgraded version is twice as expensive as the base option here. Next, we're looking into lighting controls. In the base building, we have standard occupancy and vacancy sensor lighting controls in areas where those types of controls make sense. With our upgrade, we still have the occupancy controls, but we add daylighting controls that will dim or turn off light fixtures when we have enough sunlight to meet our needs. This isn't super expensive, but the amount of daylight that you get very much depends on the building massing that we select. Here's where we get into mechanical. So our base design starts with a pretty typical VAV system with a gas boiler and an air-cooled chiller. With our upgrade, we're moving to a ground source heat pump, often known as geothermal, where we push and pull heat energy into and out of the earth, providing heating and cooling for the building. To install a geothermal system, you will need to drill several wells into the ground, which can get expensive up front, so the cost is higher than the base system. Next is HVAC controls. In our base design on the left, we have typical controls responding to the needs of various spaces based on temperature and maybe humidity. With our upgrade, we're adding demand controls, which allows us to cut back on ventilation rates and possibly set back temperatures based on whether spaces are actively being used. This could take the form of carbon dioxide sensors, which kick in when high occupant loads drive higher CO2 levels, or occupancy sensors to detect movement. This is a fairly low cost upgrade, especially with occupancy sensors, because we can tie into the same sensors used for those lighting controls. And last but not least here, we have energy recovery. And very simply, in the base design, we don't have it, and in the upgrade, we do. So in this case, we're providing total heat recovery, capturing the sensible and latent heat energy, or in other words, the heat in the air and the heat and the moisture in the air that would have otherwise been wasted through the building's exhaust air. So now that we've talked about the differences in those strategies, let's have you pick yours. This time we also included the savings ranges for each of the energy efficient options that are actual results from an energy model for this building to help you make a more informed decision. The ranges are based on what other strategies are being selected. So some strategies perform better only if they're paired with specific other ones. The strategy savings ranges also meet our first cost budget of $12. So we're looking here at how to achieve the best energy cost savings. If we were looking at EUI savings, the range would look totally different. So once more, I want to note that if this was a different building type in a different location, the savings shown here would be different. And let's give everyone a moment to return to the poll and pick their selection. Great. Okay. Looks like we do have a different layout of answers this time. So I'll continue. So let's take a look at how everyone did based on each answer choice. So we are looking at the 6 energy efficiency conservation measures with the dollar signs correlating to the basic and upgraded options for each category. The bar on the right represents the project's budget, which has a maximum of $12. So let's review the combination of strategies that you all selected. So for option A, we did the dispersed massing. We did the envelope upgrades, the daylighting controls, the VAV system, the demand controls, and no energy recovery. So let's see the results for this one. So this one ranked 25th out of 32 out of all of the possible combinations. So pretty low in the rankings, definitely some room for improvement, but still saved almost $50,000 in energy cost savings. So let's see how this compared to option B. Let's see, this one was the compact massing, the envelope upgrades, basic lighting, the VAV system, no demand controls, and energy recovery. So this one did a bit better. It ranked 10th out of 32 in energy efficiency. It's on the lower end of the EUI, and it saved a few more thousand than the previous option. Let's check out option C. So for this one, we did the compact massing, the basic envelope, basic lighting, the geothermal system, no demand controls, and energy recovery. Wow, so this one was number 1 out of 32 in energy efficiency with a super low EUI as well, and the highest energy cost savings we've seen so far. And let's take a look at option D. So this one did the larger, more dispersed massing, the basic envelope, the daylighting controls, the VAV system, demand controls, and no energy recovery. This one came in under budget. So this one, not so great as far as energy efficiency goes, 27th out of 32. EUI a little bit on the higher end compared to the one before it, but still did save $50,000 in energy cost savings. So let's look at how the different strategy combinations fared and some trends on how specific strategies played into the overall results. This is a graph of every possible outcome in this exercise, and each bar here represents the savings resulting from one combination of strategies. In total, there are 32 combinations of strategies that stayed within our budget, and if we stack them up in order, least savings on the left and most savings on the right, we can see that by selecting strategies within our budget, we can potentially save the owner around $65,000, which for this building would mean a 40% reduction in their energy bills. Remember, we want more savings, meaning lower energy costs. The dispersed form strategy is included in two of the lowest energy savings design, but is also included in some of the higher saving groups. The savings you see here are heavily tied to which mechanical system you decide to implement because the heat loss and heat gain are higher. The ground source heat pump system savings may seem a little surprising. We always think of geothermal as being the best system that you can implement. So you may think that it would have the highest energy cost savings, but those fall in the middle-ish of this group. And this is mainly because the cost of natural gas is relatively cheap right now, and this option switches from gas to electric heating. If the cost of natural gas went up and the cost of electricity went down, this grouping would change significantly. Also, if we were looking at energy use intensity instead of cost savings, this group would be among the highest on the chart. HVAC demand controls are included in groups across the board. So that leads us to believe that for this building in particular, it isn't a huge driver of energy savings. But speaking of drivers for energy cost savings, the energy recovery combinations are the top 9 on the board. This has a lot to do with the climate zone here because in this state, there are very cold winters and pretty hot summers, and we need to be able to capture as much of the wasted heating and cooling that we can. Envelope upgrades are important, but also expensive. And in order to include it in the design, often we just didn't have the budget to upgrade it. However, when we were able to afford it, with the energy recovery strategy, it added to the highest savings combination. And like the demand control ventilation, lighting controls are all over the place on the board, which tells us it isn't a huge energy savings driver. But since they are a relatively inexpensive measure to implement, it's easier to fit them into designs and could be some low-hanging fruit. When you have a lower budget, you would typically think that means you won't be able to save as much in energy, which is generally true, except you can use an energy model to develop a scenario where you can actually have significantly more savings if you look at different options outside of what you normally may have thought. Of course, the cost of energy efficiency measures can affect the project budget. An energy model can help identify the most cost-effective group of energy efficiency measures. Here, relative costs are overlaid on the measure combinations. Overall for this project, costs trended upward as efficiency improved, but it wasn't linear. In some sections of the chart, costs trended downward as efficiency improved. And if you're working with a budget range, an energy model can help find the sweet spot of lower costs and higher efficiency. So what did they do for the actual constructed building? First, let's remember the optimal time to maximize on savings would be during schematic design and design development. First, by taking steps to minimize the energy load, then followed by the implementation of simple, cost-effective systems. Of course, by the time a building becomes occupied, it's key to remember that people may run that building in ways that we did not imagine during design. And now, what option did the project team choose? Out of the 4 options we gave you earlier, this is the one that they chose, focusing mainly on controls, daylighting, and HVAC demand controls. Here are the strategies they selected on this project: the dispersed form, the basic envelope, daylighting controls, the VAV system, demand controls, and no energy recovery. And the reason they didn't do energy recovery was due to maintenance concerns. And here we can see how this project's design played out compared to other options that might have been considered. Not so great on the energy cost savings, $34,000, and the EUI wasn't that impressive either at 61. Although they did fairly well with peak savings, overall, there's still a lot more potential for the project as we learned through the exercise. Eventually, the school decided to switch from the VAV system to the geothermal heat pump. It just took some time for the facilities director to get comfortable learning that new system. And we should note that by making this upgrade, the school spent additional funds and did exceed their budget. In terms of the bundle performance, the geothermal upgrade shifted the school up to 15th place. The energy cost savings increased to over $43,000 a year, and the EUI also improved. After construction, we were able to look at their meter data and compare the actual energy use, shown in green, to what was originally modeled, shown in blue. So why was the actual energy use higher? There's a couple reasons. One, we had originally anticipated the hours of operation to be less during the summer due to school being out. But it turns out the community liked having a fresh new building, and they wound up using it a lot more during the summer for different events. And two, another factor of the increase energy use was that they had disabled all daylighting controls after they got a complaint from one teacher whose lights weren't working correctly. So the good news is that after they realized that and the controls recalibrated, they were able to start using those controls again. So if you've learned that energy use of your project has changed, there's no need to panic. Here are some common reasons we've found as to why the meter might be different from the model. Maybe the hours of use have changed, or the space might be being used differently than what we anticipated. If you don't anticipate higher plug loads, or if the controls have been overridden or the calibration is off, or if there's equipment malfunction, which is rare but does happen sometimes. And as we're wrapping up, here are a couple of key takeaways when evaluating a project's energy potential. With every project being different, it's important to establish those energy goals early in design, especially when utilizing model data to support your design decisions. Partnering with your electric providers helps you take advantage of energy consulting services. And of course, it's key to remember that people run buildings differently than expected. And here's a quote that we'd like to leave you with today by Donald Watson: "Energy is a design topic, not a technology topic." This is a good reminder that energy use is a challenge that's in the hands of the project team, and there are tools available to help solve it. Awesome. And at this time, the team would be happy to answer any questions.
If you have a question, feel free to either put it in the chat or you can unmute yourself and ask away.
Awesome. Well, thank you everyone for your time today. Again, I'm Sarah on the Willdan outreach team. You can reach out to myself, Annie, or Han at any time with any questions about the presentation or about the commercial new construction program. And thank you for joining.
Thanks, everyone.